Okay, so first off, you guys can ignore these ones. I have assigned different questions and they are at the bottom or at the end of this video. We're going to talk about anti-differentiation by substitution. So we've been doing anti-differentiation for both definite integrals and indefinite integrals. So they both share the term integral. They're two unique things. So definite integrals give us the area under a curve through finding the limit of a sequence of Riemann sum. So approximation by smaller and smaller and smaller rectangles between 2 points. So if you have something like this, A to B, you're adding up all of the little baby rectangles as those rectangles get super small and there's infinitely many of them. An indefinite integral gives us a family of functions that have a common derivative. So indefinite integral would just be the integral without boundaries, and that's where you're going to see that plus c that's going to move that function up or down depending on what the c value is. It's basically a vertical translation or k value. This one's going to be a specific area with a and b values. Okay, so below is a list of common integrals, most of which will look familiar. So I went through this, not in a ton of detail yesterday, but hopefully in enough. So the integral of cos, for example, is sine x plus a constant. The integral of e to the x is e to the x, so it's basically the opposite of a derivative. Okay, so a couple examples. So we've got the integral of 2 sine x minus 3x to the 4 dx. Okay, so basically we're doing the antiderivative of both of these. We're looking at our integral chart. Remember that the 2 can come out in front, and then we're looking for the integral of sine x. So if I have this beside me here, the integral of sine x dx is negative cos x. So this would be negative cos x. And then minus the 3 can stay. And then when we have an x to the 4, remember that the antiderivative would have started as a 5. And then that 1/5 is going to have to be there for when that 5 comes down to multiply. Okay, and then we're going to add that constant, that's that shift between all of these functions that could exist. So this thing, if we simplify, is going to be negative 2 cos of x minus 3/5 x to the 5th plus c. Okay, so that x to the n, right, in this case n was 4. It's going to be x to the n plus 1, so that's how we got the 5 over 5 plus, or n plus 1, so again, that's a 5. So that's how we get that part. If we're doing the integral of 4 over x minus secant x tan x plus e to the x, so we're just looking off of our formula sheet. So if we've got something, so either just a dx or a number over x, remember that that's going to be ln x, because the derivative of ln x, if we take the derivative of that, we get 1 over x. Okay, so if we go backwards, this thing is going to be 4 and then ln x. If we want to do the integral of secant x tan x, I'm going to look at my formula sheet, and hey look, that combination is here. That just is secant x. Oh, and if that's a negative, then this is also a negative. And then plus e to the x, the integral of e to the x is e to the x. And then from that we have to add a plus c. Okay, so we're seeing how we can use our formula sheets to figure out the integrals. The more you practice this, the more you're going to know what to look for. to find an indefinite integral from a function whose derivative included a chain rule, things can get pretty complicated. So we use antiderivative or antidifferentiation by substitution, the title of the lesson, to help deal with this problem. So, for example, finding the integral of this thing, so 3x squared plus 2x times e to the x cubed plus x squared looks really intimidating, okay? However, if we use substitution, if we make a different letter, typically we use u. If we turn that into x cubed plus x squared, and we'll talk later on about how I need to do that, okay? Then if I do the derivative of u with respect to x, then that would be 3x squared plus 2x, right? So I'm doing the derivative of this guy, so I get that. If we rearrange the latter, so this is du divided by dx. If I multiply both sides by a dx, then I'm going to have a 3x squared plus 2x all multiplied by dx. If we rearrange the original integrand, we can find the following. So if we write this as e to the x cubed plus x squared times 3x squared, may as well put that one in brackets too, plus 2x times dx. Notice how, I guess not that whole thing, this whole thing up there, that's what we decided u was. And see how that whole thing is now du. So now the statement is rather easy to integrate, because if we substitute in u and du, we just have e to the u du. And then if we look at our formula sheet, we can say, well, the integral of e to the x dx or e to the u du, that would just be e to whatever variable. So in this case, u. So this is e to the u plus c. Now we can just substitute the x's back in for the u, so e to the x cubed plus x squared. Okay, so when we still need that plus 3. If we want to check this, if we do the derivative of e to the x cubed plus x squared, it's going to be, the derivative of e to the something is always just e to that something. So e to the x cubed plus x squared, and then we'd have to use the chain rule, do the derivative of that exponent. That's where we're getting that 3x squared plus 2x. Okay, so that's how we use substitution. Now, sometimes in the world that is really nice, it's going to give you what your u value should be. Okay, so the first bunch of practice problems, they're in the textbook, give you a u value. Same with this one. Other times you're going to have to figure out what that u value is. The more you do this, the more you'll be able to do that and recognize what should be u. Sometimes it's just a trial and error. So, in this case, we have u is equal to 3x. It tells us that. What we always want to do once we found our u is figure out what du dx is. So what's the derivative of u with respect to x? In this case, that's going to be 3. Okay? And then if we multiply both sides by dx, oops, don't cancel over there. That one stays. Then du is going to be 3 dx. Okay? So, what we need to do here is we're doing sine of 3x. Okay, so this is going to be the integral of sine u, because that 3x, we're going to substitute in that u. And then we need to just put dx here. But the problem is that we don't have dx by itself. So we're going to have to divide both of these by 3 to figure out that du divided by 3 is equal to dx. This whole thing can go in for that dx. It's going to be du divided by 3. That divided by 3 is just a constant. That's a 1/3. So we could pull that out right away. And then we just have 1/3 times the integral of sine u du. Okay? Then we're looking at our formula sheet and we're saying, okay, the integral of sine x dx or sine u du, as long as the variable is the same, it doesn't matter what it is negative cos plus c. So negative cos of u plus c. And then if I put my x's back in, this is going to be negative 1/3 cos 3x plus c. Now why I don't need to distribute that 1/3 to the c is that c is just a constant. It doesn't matter what it is. So if I pick 9, if I pick 17, if I pick 27, it doesn't really matter. That 1/3 is just going to multiply with it, and it's still just a number. It can be anything. Okay, so we don't actually have to write like 1/3 c, even though that would be the more proper thing to do here, because c is just a placeholder. Okay, so as a check, now my function is negative 1/3 cos of 3x plus some constant. If I do the derivative of that, then it's going to be that negative 1/3 stays out in front. The derivative of cos is negative sine of whatever's in there times the derivative of 3x. So in that case, it's going to be 3. And then the derivative of c is just a 0. So that's why it doesn't really matter what that 0 or what that c is. Okay, so then we have negative 1/3 and negative 1 multiplying. Those cancel, and the 3 and the 3 cancel. So we end up with sine of 3x. Okay, so that was our original. So that we've done that right. We're going to find the integral of sine x times e to the cos x dx using a substitution of u equals cos x. Okay, generally whenever there's an e to the something, whatever that something is, that becomes our u. Okay, so we're saying u is equal to cos x. Then du dx would be equal to the derivative of cos is negative sine x. So then du by itself, if we multiply both sides by dx, is negative sine x dx. So then the integral here, I'm going to rearrange it a little bit. So e to the cos x times sine x dx. Here is my, or I guess it's e to the u, and then times, notice how again, to get this, I need to multiply the negative across and get negative du is sine x dx. So we're looking how we can substitute this out and get a du in, even if there's some numbers attached to it. So times negative du, and so then this whole thing just becomes negative e to the u du. So the integral of that is just e to the u, and then you should add the plus c there, so that when we substitute our x back in, we're going to get negative e to the cos x plus c. So the check y is equal to negative e to the cos x plus c. If we do the derivative of that, then the derivative of this thing is itself, because it's an e to the something, and then times the derivative of the cos x, which is the negative sine x, and then the derivative of that c, that constant, is going to be a 0. So negative times negative gives us a positive, so this is e to the cos x sine x, which is what we had to begin with, just in a different order. Then we're going to do the integral of x squared times root 5 plus 2x cubed using a substitution of u equals 5 plus 2x cubed. So generally, if there's something under a root or as an exponent or in a cos or a sine, that's what you're going to use as your u. So see how this is the under the root thing, and that's what we're using. So u is equal to 5 plus 2x cubed. So then du dx, the derivative of 5 is just 0. The derivative of this guy is 6x squared. So then du would be equal to 6x squared dx. Okay, so our integral, I'm going to rearrange the order here. We're going to have the root of 5 plus 2x cubed. So that whole thing under that root can be replaced with u. And then we've got x squared dx. So notice how only this is there. So we need to divide both sides by 6. So now we can sub in du divided by 6 for this whole thing. So then this is going to be root u times 1/6 du. So that whole thing, that 1/6 can come out in front, and then we've just got the integral of root u du. So if we've got the integral of root u, actually in this step I'm going to rewrite this as u to the 1/2. So that 1/6 is going to stay out in front. And then this one is an exponent rule, so we can use this formula. So in this case, n is 1/2. So the integral is going to be, we're going to have a 1 over 1/2 plus 1 is 3/2. And then u to the 1/2 plus 1 is 3/2 again. So this is going to turn into 1/6. 1 over 3/2 is the same as 2 over 3. And I forgot my plus c. I tend to do that. So we can simplify that a bit. So we're going to have 1 over 9 u to the 3/2 plus c. And then if we substitute our x's back in, 1 over 9, this is going to be the square root of this whole thing cubed. So I'm just going to leave it as to the 3/2 because that's going to be easier. We could convert it to root because we know how to do that. So 5 plus 2x cubed to the 3/2 plus c. So if we want to check that, we have y equals 1/9. 5 plus 2x cubed to the 3/2 plus c. And we do the derivative. That 1/9 is going to stay out in front. That 3/2 is going to come down. What's in there is going to be left. 3/2 minus 1 is 1/2. Then multiply by the derivative of what's inside here. So it's going to be that 6x squared. And then the derivative of c is 0. So then when we simplify, we've got 3 times 6 as coefficients on the top, and then 9 times 2. Both of those are 18, so that's all going to simplify to just a 1. So then we're going to have, all of my coefficients are gone. We're going to have 5 plus x cubed to the 1/2. So 5 plus 2x cubed to the 1/2 times x squared. So if we rearrange that, we get what we started with. Okay, so you can always check. This one we're not going to worry about for now. It's basically just substituting functions into other functions. I'm not going to ask you guys a question like this. You'd be capable, but we're going to skip this one. Number 6, we've got find the integral of ln to the 6. So same with cosine, sine, and whatever. If you see an exponent there, that's the same as ln x all to the 6 over x, using an appropriate substitution. So generally, I'm going to rewrite this as the integral of ln x to the 6 over x. Generally, if you see something like this to the 6th or something inside something else that's complicated, whether it's under a square root or in a cosine sign or being raised to an exponent, something like that, it's a really good idea for your u. So I'm going to say u is equal to ln x. Then du dx would be equal to the derivative of ln x is 1 over x. So then du, if I move the dx over, is going to be 1 over x times dx. Oh, I forgot the dx there. So notice how we've got ln x to the 6th, so that's going to be u to the 6th. Then we've got this is a 1 over x dx. So then we can substitute just a du. This whole thing is that. Then this is really easy to do the integral of. So it's going to be 1 over 6 plus 1 is 7. U to the 6 plus 1 is 7. And then plus that c. So then we get 1/7. We plug our ln x back in. Ln x 7 plus c. Okay, and we could do the check if we wanted to, just like we have been, but just for time, we're not going to do it. Find the integral of sine 2x plus 1 over cos squared of 2x plus 1 dx using an appropriate substitution. Okay, so if you've got something inside a sine or a cos, generally that's going to be it. Okay, so on something like this one, we use what was inside of that sine as our u. Notice how on this one, we've got sines and coses both with the same thing inside. So if they both have the same thing inside, that tells me that it can't just be a u equals 2x plus 1. Okay, what I see here though is I see a cos squared of this thing. So this whole thing on the bottom, cos of 2x plus 1, that whole thing is squared. So I'm going to rewrite this as sine 2x plus 1 over cos 2x plus 1. That whole thing is squared dx. So what I'm going to make my u is that cos of 2x plus 1. Okay, because that whole thing is getting squared. Then if I do the derivative of this thing, this is going to be the derivative of cos is sine, and it's a negative sign. No, yes. Derivative of cos is negative sine of that same thing multiplied by the derivative of what's inside, so 2. So du dx is going to be negative 2 sine of 2x plus 1. And then if I do this whole multiply both sides by dx in the same step, it's going to be like that. Okay. So we have to figure out how to get that by itself. So this, see how this whole thing is u? So on the bottom, I'm going to replace with u squared. Then this whole thing, so that's this part. So because that's not by itself yet, I need to make it by itself, divide both by 2. And now I can replace this whole thing with the du divided by negative 2. So then I'm going to simplify a little bit. Okay, so du divided by negative 2 is going to be, I'm going to write that as negative 1/2 when the du out in front. And then the u squared on the bottom, I'm going to write that as u to the negative 2 on the top. Okay, so the order of that wasn't the best, but the negative 1/2 is going to come out in front, and then we're doing the integral of u to the negative 2 du. So if we do the integral of that, that negative 1/2 is going to stay out in front. We're going to have, so this is this rule here, okay, so a u to the negative 2, if we're integrating that, we're going to have u to the negative 2 plus 1, which is u to the negative 1 over that negative 1, and then plus c. So negative times negative, those cancel out, so this is going to be a positive 1/2 u to the negative 1 plus c. We could write it as 1 over 2u plus c. If we wanted, that also is fine. Okay, and then we could, oh, I forgot to substitute the x's back in. These are not my final answers. Ignore those. Okay, so then it's 1 over 2. U was cos 2x plus 1 plus c. There's my final answer. Next one, we're going to do find the integral of 3 sine x to the negative 2 dx. Okay, so first thing I'm going to do is I'm going to take that 3 out. And we have to think about what we're going to use here. So we've got something to the negative 2. That's certainly complicated, but the derivative of sine is cos, and there's none of that showing up anywhere, so that's not the best substitution. So if I look at my formula sheet here, there's nothing with sine x squared, or sine x to the negative 2, but we do see something with cosecant and secant squared. So if this is to the negative 2, remember that that's happening twice on the bottom. And then the reciprocal of sine is cosecant. So sine squared x on the bottom is the same thing as cosecant squared x on the top. So I'm actually going to replace this whole thing with 3 cosecant squared x dx. Okay. And then this one, at this point, we don't need to do a u substitution. This substitution, like an identity, a thing that we knew from before, is enough to make this thing easy enough that I can say, okay, well, the integral of cosecant squared x dx is just right here. It's going to be 3 negative cotangent x plus c. So negative 3 cotan x plus c. So that's all I needed to do for my substitution there. So sometimes they can be identity substitutions instead of a u substitution. It's like, how can I make this thing easier? Okay, we're going to do one more of those with both types of substitution. So if we have a sine cubed of 2x dx, we're going to use this trig substitution first. Okay, so this is the same as, if we have sine cubed of something, that's the same as sine of 2x times sine squared of 2x, right? Because the something times something squared is that something cubed. Okay, notice how this is equal to this. Can't forget my dx. So I'm going to substitute, I'm going to leave that sine 2x, and then I'm going to multiply that whole thing with 1 minus cos squared 2x. And generally, if it wants you to do something complicated like this, it'll tell you. And so then you don't look for your u's and your du's until you've gotten to a point where it's simplified. Then I'm going to distribute this thing in. So I'm going to say, okay, this is the integral of sine of 2x minus sine 2x cos squared 2x, and that whole thing gets the dx. Okay, and then this can be just split into two separate integrals. So this is the integral of sine 2x dx, and then minus the integral of sine 2x cos squared 2x dx. So now we need to look for what our u and du are going to be. So since we've got a cos 2x squared, I'm going to make my u cos of 2x. So I'm going to look at kind of the most complicated thing here. I'm going to look at that. Then du dx, the derivative of cos is negative sine times of the 2x, and then times the derivative of what's inside, so 2. So then du is going to be negative 2 sine 2x dx. Okay, so notice how I've got my sine 2x dx. I just need to divide both of those by negative 2 to replace that part. Okay, so this can go in for that part. This can also go in there. So we're going to have the integral of, I'm going to write it as negative 1/2 du minus the integral cos squared x, that's u squared. And then this whole thing, the rest of it, is negative 1/2 du. So that negative 1/2 can come out in front. And then we're just doing the integral of du, which seems perhaps complicated, but it's really not, promise. And then that negative 1/2 can come out again, so this is going to turn into a positive. And then u squared du. So the integral of du, that's basically just a 1. So the integral of 1 would have been 1x, right? Because the derivative of x is just 1. So this is going to be, and in this case we're talking u, so it's going to be just u. So it's going to be negative 1/2 u plus 1/2 of, this one we're going to use that power rule, so 1/3 times u to the 3. So 3 would have come down, multiplied with this, it would have canceled out, that would have ended up as a 2. And then plus c. So we're going to have negative 1/2, the u can get substituted back out with cos 2x plus 1/2 of, I guess I should turn this into 1/6 cos 2x cubed plus c. Okay, so without that trig substitution, this thing would have been absolutely crazy. So whenever it has a trig substitution, trust it, use it, simplify as much as you can. If you can, split it into two more simple ones. They should still work with the same u and du. Okay. This is the only definite integral. We've been doing lots of indefinite, but this is the only definite one that we're going to do. So this one does have boundaries, and so we're going to look at what that looks like. So the first thing that we're going to do is I'm going to rewrite this. This 10 can come out in front. So this is the same as 10 times the integral from 0 to 1 of root x over 1 plus x to the 3/2 squared dx. Okay, so what's under here is an x. That's not super complicated, root x. We've got this whole thing squared. So what we're going to do is we're going to make u that whole thing. So 1 plus x to the 3/2. And sometimes this is just a trial and error. When we do this, when we do the derivative of this, hopefully it's going to tie this in somehow. So then du dx is going to be The derivative of 1 is 0, and then the derivative of this is 3 squared x to the 1 half. 3 squared, 3 halves x to the 1 half, which is the same. This thing is the same as root x, right? So I could have written that as a x to the 1 half there. So see how now we've got, if I rearrange this, I've got du is equal to 3 halves x to the 1 half dx. So this part is taken care of. This part is taken care of. We just need to get rid of that 3 halves for when we substitute it in. So divide both of these by 3 halves. So this is going to be, divided by 3 halves is the same as multiplying by 2/3. This is going to be 10 from 0 to 1. Now at this point, because I'm substituting u's in, I like to write x equals and x equals, just so I remember that these are x's, right? These 0 and 1 are attached to x's. If I plug a 0 and a 1 in for the u values without putting my x's back in, I'm going to get this wrong. So I like to give myself a little note. X is equal to 0 and x is equal to 1 are the boundaries, so I don't get confused. So this is going to be 1 over u squared, and that's this part, times this whole thing gets replaced with 2/3 du. Okay, so that 2/3 can come out, so then we've got 20 divided by 3, x equals 0 to 1. Don't even have to write it on both. And then we've got u to the -2 du. So now this is easy enough to integrate. So I can go from 20, so I've got 20 over 3 from x equals 0 to 1. No, I didn't need that anymore. Oops. Doing the integral. So then this is going to be multiplied with the integral of this thing. So is going to be u to the -1, because when it dropped, it must have ended up like that. And then that -1 must have been there. And that's going to be evaluated from x equals 0 to x equals 1. So this is where we can't just plug in it in here because there's no x's. So this is going to be 20 over 3. I'm going to rewrite this as -1 over u from x equals 0 to 1. So this is going to be the same as -1 over, remember that u was 1 plus x to the 3 over 2. So when I do that, I'm going to have 20 over 3. Remember, we take the top one and then multiply the bottom value. So this is going to be -1 over 1 plus 1 to the 3 halves minus -1 over 1 plus 0 to the 3 halves. So this part is going to be 1 plus 1 is 2, so -1 half. And then this is 1 plus 0, so 1. So this whole thing is just a plus 1. So then we simplify. -1 half plus 1 is +1 half. +1 half times this whole thing is 10/3. Okay. The other way that we could have done this, so from here, and if you're out of room on this, you don't necessarily have to write this down. So we could, or instead of plugging in x's here, we could figure out, okay, when x is equal to 0, what's u equal to? So when x equals 0, then u is equal to, we can plug our x values in here. So if x is equal to 0, u is equal to 1 plus 0. So u is equal to 0. When x is equal to 1, u is equal to 1 plus 0 is not 0, this is 1. if x is equal to 1, it's going to be 1 plus 1, so u is equal to 2. So the other thing that we could have done is left it like this. So 20 over 3 from u is equal to 1 to 2, because those are the corresponding values of negative 1 over u. Or no, not like this. We've already done the integration. From u is equal to 1 to u is equal to 2. So you can evaluate it like that as well. So 20 over 3, we've got negative 1 over 2 minus negative 1 over 1. This whole thing is also equal to 1/2. So you get the same thing. Right, so I like this better. I just find I make less mistakes. You can do it in terms of u if you plug the x's in to get the proper u functions. Okay, so either way, whichever way made more sense to you. For today, here's your practice. I didn't do it day 1, day 2. So for today, start on it, do as much as you can. Tomorrow we'll do some Q&A, and I'll do like a quick check-in question. So just a little practice. It'll be for a mark, but it won't sway your marks in any way, shape, or form. So that's what you should practice. And if you have any questions, either send me an email or you can wait on them until our hangout tomorrow. Hope all of that made sense.